Hello, we're back again. It's Professor Elliott, and this will be JFET lesson number 2. We will talk about drain curves. In my first video, I introduced to you the JFET, N-channel, P-channel construction, IDSS, VGS off, just some basic fundamental terminology, and we're going to build upon that in this next video. So this again is known as the drain curve, and it just shows the relationship between the drain to source voltage and the drain current ID. So just once again, okay, right now this applies equally no matter if you're looking at the N channel or P channel, but we'll just stick with the N channel because that's what I'm focusing on. And okay, so that is the N channel. So this is going to be the drain to source voltage, VDS, and this is going to be the drain current. Okay, so that as a little memory aid, poorly drawn, but anyway, there you go. And it says that if you make the gate to source voltage equal to 0, that sets the conduction channel width to a maximum, and you have the saturation current IDSS. And again, that's a data sheet number. We looked at that last time. Okay. And the intersection of IDSS, okay, and the drain to source voltage is this red line here. That's called VP, and that's known as pinch off. Okay. Now what happens is you don't always want the current to be at a maximum, so you can have the current to be constant. So this is the linear constant current area, but it's going to be less than IDSS. So just literally making up some numbers here. If that was 10, okay, so maybe then we want the current to be 8. So then this would be like this, okay. And then this curve would be more like, yeah, can I undo that? No, I can't just undo that. And it'll come up there. Ah, I really messed that one up. I have to erase that. Let's try this again, okay? And, okay. And then this is going to be like kind of like that. This would be constant like there, and then kind of join up to there. Okay, so you can have the current constant, but at a current less than IDSS, which is fine. And but then this VP is at a different voltage because these two intersection points are different. Okay, so does it matter? If you're designing it, it does. But basically, you can have the current to be constant at different current levels, and it's only saturated when the current is at IDSS. That's sort of the maximum point. Okay. Now this pinch off voltage, I know this is confusing, and I hesitate to mention it. Every time I've mentioned it with students, eyes have glazed over. But anyway, this pinch off voltage technically only applies to IDSS and VGS off equal to 0. So it's at that data sheet defined point where the conduction channel is wide open. If the conduction channel is not wide open, but the current is constant, we still have VP, but it's not called pinch off anymore. Um, it's because it's the data sheet, because it's not a VGS equals to 0. Okay, so the voltage is constant, but it's not at this pinch off voltage, which only applies when you have this and VGS equals to 0. Okay, so anyway, the most important thing is that you can put the JFET or the MOSFET in the constant current area, and the drain current is going to be constant at a particular level, and of course that will then change the drain to source voltage. Okay, so anyway, okay, so over here, so this is the circuit to derive that curve. So we literally ground the gate. Again, this is the drain, and this is the source, and then that forces VGS to be equal to 0 volts. In our little example there, then that would mean that our drain current is equal to 10 milliamps, which would be IDSS. Okay, so that's totally dependent on the JFET device you have in your hand. Okay, but that's at that particular point, and this means it's the wide open conduction channel width. Drain current is at a maximum. Okay. Okay, once again, just review of the basic terminology. Okay, IDSS, again, this is like saturation. Okay, this is the maximum drain current, and as I mentioned earlier, it only applies under that condition. Okay? And this comes from the data sheet, and we looked at that in the last video. All right. Okay, all right, so again, IDSS, this is the saturation, this is at a maximum, this is the pinch-off voltage here, and our gate to source voltage is equal to 0. Okay, transconductance curve. Okay, as I said in the other video, you can, by just knowing the IDSS for your transistor and the VGS off for your transistor, you can calculate data points and then plot this curve. So you can see then when VGS is equal to 0, this is the, wide open conduction channel width. And when VGS is equal to VGS off, the transistor's in cutoff. This is really hard when my cat is kissing my pen and I'm writing, is that this conduction channel width now is very narrow and the current now is less. Okay. P channel, okay, just flip the curve the other way because the gate to source voltages are positive, but it operates the same way. Okay, points A and B are the saturation and cutoff points respectively. Okay, again, this is the equation. So that's from the data sheet. This is from the data sheet, and my cat here just loves anything with a mouse pointer. Willie, can you catch it? Can you catch it, Willie? Want to say hi? Willie says hi. And then you just simply change this number. I usually start at 0. It goes 0, 1, 2, 3, 4, 5, up until this voltage here. But the more steps you do, the better. And then you calculate it, and then you just graph that curve. Okay, so here's an example. Assume our saturation current is 6 and our cutoff voltage is -5. So this is our conduction channel is wide open, current's at a maximum. Conduction channel is closed, our current is 0. There is some leakage current, but okay, can't totally get away from that. So start at 0, then -1, -2. The more steps you do, the better. Okay, and then this is the cutoff voltage. So calculate all those, and then just simply then just plot them. Okay, and if you're going to do this, use best fit average and not point to point. Okay, so was that it? All right, that's it. We will continue on with our next video with Willie helping. I think we're looking at JFET self-biased. Okay, all right. Thanks. Cheers.